Hi again. Welcome to part 2 of the application layer module. And in this module, we're going to be talking in more details about the HTTP and like all the protocols and all the details of the protocol. And to start the whole discussion, let's talk about, just to introduce a few things about HTTP and how things are working internally. And for the discussion, just assume a very, very simple model for the web pages. In today's environment, they're way more complex than in this basic model, but just assume what we have. And the basic model is just one simple HTML page, and that HTML page includes different references to few objects. In today's environment, there's still a single HTML page that you're retrieving first time, and that page refers sometimes to hundreds or sometimes even more external objects, and those external objects can refer to another external object and so on. But I'll try to talk about this a little bit more later. And those external objects can be in other HTML pages, images, audio file, video file, and so on. And one important and actually critical element and kind of the fundamental element of HTTP is the fact that every single object is being referred by the so-called universal resource locator, or in short URL. Most likely, I'm sure that you have seen tons of different URLs, and you probably recognize some parts. But there's a few things that have been put as part of this HTTP or just as part of the URL that you need to know about. So the first part is a scheme, or sometimes it's also referred as the protocol. And normally it's either HTTP or HTTPS. The browsers a few years back, they actually were showing you this HTTP part, and kind of the modern part, modern browsers decided not to show you and only indicate whether it's secure or not secure. Besides HTTP, there's other protocols, and which I used quite extensively outside the HTTP and kind of web realm. So the other part is so-called authority. You can also call it a host name, but the proper name for that one is authority, which technically contains two parts, or can contain two parts. One is the host name that you can see on the slide, and the other one is port name. There's actually an optional element that can be put just right here, just before this www, where you can include username and password. So sometimes it's being used in web applications. This usually not used that much. Maybe username sometimes used, but not more beyond that. So the third part of the name is the path name. So this one effectively indicates the resource name on that server identified by the authority that is retrieved by the protocol defined by the scheme. And the last part, this fourth part, is some kind of clarification of something about the resource. You can call it a fragment, you can call it a query, and the interpretation is quite different depending on what kind of the actual page is about. If it's a static page, if it's a static HTML page, there's not really a query, like you cannot query anything about static, but you can use the fragment part to indicate which part you want to scroll down to a specific kind of link in the page. If it's a dynamic, both of this query and the fragment can be used by whatever means necessary that is defined inside the application. I'm not going to talk about this more, but just remember that there's four important parts of the URL that being used everywhere. And the key point to remember from this slide is the fact that everything is addressable by URL, because this will be actually very important to support so-called the data centricity of HTTP that we're going to be talking in the next part. And just to highlight what you can do, what you can see as part of, as I said, very simple website. So the extremely simple website can be just this amount of HTML code that has some text, some tags, and have references to external, not external files, but additional files. So one thing that you may notice here, so I put the URL of the page like this, and there's also URLs of the images like that. But I didn't actually use the URL full URLs as part of all these references inside the page, and for one specific reason. There are a few assumptions inside HTML to allow you to refer to something current. So for example, this one not only refers to the resource on a specific server, but also under the same path as the index.html, so, as the parent, the actual page that you're referring to. So for example, if it was somewhere in the root folder, then it will be, assuming all the previous part of the URL is exactly the same as the kind of requesting page. If it was something else, as maybe you can actually decipher what is written on the picture, then the URL for those pictures would be quite different. There will be HTTP, web, cs, ucla.edu, and like long path, and kind of the last part of the path, this one is assuming to be index.html. It will be simply replaced by the name of the image. But at the same time, you can also specify the full URL. So for example, in this case, I specified that I want to refer to HTTPS, and some hosting happened to be Wikipedia, and some path towards the resource. In this case, I'm asking about Yellowstone National Park. So that's kind of the whole point. So everything addressable, everything within the HTTP protocol is addressable by this magical URL. But that's kind of not the whole story. The whole story starts with the fact that HTTP kind of operates in terms of this magical URLs versus IP. If you kind of look forward and look back to our initial introduction in Module 1, operates on IP addresses. And even in Module 2, I talked so far was only about some kind of BSD sockets, maybe at most the host name. But there's nothing about the URL, about the request, about anything else. So this is where HTTP actually coming from. So in order to run, or in order to do the web application, you actually have to do work on the level of HTTP protocol, meaning that there has to be server running HTTP protocol, and has to be client that understands HTTP protocol and can kind of connect to the server, issue HTTP request, process HTTP response. And in a simple case, it's for the client side, it's a browser that requests some information, some web objects, images, pages, and the server side simply serves those objects. In more complex cases, the server is doing a lot of stuff. Sometimes client also do some client-side processing, and so forth. So, as I said, there's a concept of HTTP requests, HTTP responses, and one thing, again, to remember from this is you have to establish TCP connection first. So all communication, all these request responses actually happen within TCP connection. And as I will be showing a little bit later, you establish connection, that's kind of some exchanges for that. Then you send the request, process reply. And as the history progressed, there was initial specification, that there was a revision of the specification, how this HTTP protocol is supposed to operate. So one of the initial versions, the first version of HTTP, defined a very simple model. And that model was you want to get the object, you establish TCP connection, you send one request, you got the HTTP response back, connection ended. If you need something else, if you want the second request, if second object, then you have to establish new connection, send a new request, and get the response back. As we will talk a bit later, that was not ideal model for several different reasons, one that we will talk in more detail a bit later. So the modification, one of the important modifications that were made to make it a persistent connection, which means instead of every time establish a new connection, if you want to request some object from the same server, you can just keep the same connection. So you establish TCP connection once and you request multiple times. And the pipelining is actually additional technique on top of the persistent connection, where instead of sending a request, waiting for the response, sending a request, waiting for the response, like going sending and waiting, sending and waiting, sending and waiting, you can in some in some environments, it's more efficient if you send multiple requests at the same time and then just collecting data as it's coming in. So it's effectively called the process of this, if you send multiple times at the same time, called the pipelining. To give you more details about the history of HTTP and the progress towards the future, we'll talk a little bit more about HTTP 2 and actually a successor of HTTP 2 in the next part. But you can already can watch this small YouTube video that explains some of the details about the history of HTTP. So this one is linked here and also in Canva's additional reading page, an additional reading section of the module 3. Getting back to kind of basics of the HTTP protocol that I already highlighted in some way. So we have TCP connection, and in kind of in simple form, it's the client establishes this connection and server accepts TCP connection. All exchanges are happening within that, and we use HTTP messages. So this is the specially formatted messages that is understood, like all the boundaries of those messages are properly understood between the server and the client, so they know how to interpret all those things and what's supposed to be in them. And for the HTTP connection, it's either closed after a single exchange or kept alive if we're using 1.1, and we explicitly request that as part of the protocol exchanges, as part of the HTTP request. We specify a special flag to ensure that the connection is not being closed immediately. One interesting part of HTTP protocol, as of the design of HTTP protocol, was the fact that HTTP by itself is a stateless protocol. And what I mean by that is when you have an object to request, so you have a kind of URL for the object. You send this request towards the server, you got the response back, and the server technically on the HTTP protocol side have no knowledge that any of this action have happened in the past. So if you can probably request the same object again and again and again. So kind of the model on the HTTP protocol side, there's no any kind of record of things happening. This one a little bit opposite of TCP, where TCP, when you establish connection on both sides, like for the client and for the server, you actually allocate a few resources. Like you remember what, like we will talk about more, but just to highlight, you record what's the sequence number of the server records what the sequence number of the client, and then like while you start sending data, all this information being updated properly, so you server and the client knows about each other and about each other's state. So this is kind of effectively the statefulness of the TCP. And the same thing doesn't happen with HTTP protocols. It's you request, response, and no state kept at the server. This creates a great advantage for the kind of development of the servers because you don't really need to have additional memory, but also creates a few problems because sometimes you still want to kind of correlation between states. But we'll talk about this more again in the next module, not the next module, but in the next part of this module, where we're going to be talking about application statefulness. But it's again not part of the base protocol specification. Now, a little bit more details to the actual messages that being exchanged. As you will see later when we're going to be talking about SMTP, a lot of the protocols have the same structure on the wire. And what I mean by the same structure, there was decision made long time ago that the protocol as part of the message exchange has to be presented in a human readable form. I don't know why they decided to do so, because it's not really efficient. And the structure has to be in the way. So there's this first line defining the actual request, and it has to have a few specific items included. So one of them is a method, like what we're doing. So the most popular one is get method, and I'll have a few more options for that. Then have to specify the URL part, and this one is actually not the full URL, but rather path, query, and the whatever the rest fragment part. So it doesn't include the protocol, doesn't include the host name, and for a few reasons that I will just mention. Then there is a specification what the type of the protocol I'm requesting. In most cases, it would be either HTTP/1.1 or 1.0, depending on kind of what protocol you're going to be running. And it has to end with the 2 characters, not just with a carriage return or line fit character, but also this so-called carriage return character. So it just have to be these 2 characters added to the input. And what follows afterwards, again, it would be lines. Each of those lines have to be formatted in a way there is some attribute and the value. Attribute colon value, attribute colon value. And each of these lines have to be ended with this /r/n, like a carriage return and line fit characters. That's kind of the basic format. Now, getting back to why there is no full URL included as part of this request line. So for one simple reason, it's absolutely unnecessary to do so. And just remember, the first schema actually defines what the underlying protocol we're going to be communicating over. So it's either HTTP, HTTPS, or maybe something else. For as long as we're already able to connect to the server. So this HTTPS, HTTP actually defines the connection part, like TCP low-level stuff. As long as we're already connected, we don't need to specify anything. So it's from the perspective of the server, no longer it's interesting what is happening. Why the host name is not part of this URL in this particular case, I don't know. Like they somehow decided that it's not necessary, but they still included it as part of the header. So for example, you still have to, like if you're, for example, doing something manually, you still have to include it as part of the host. Like this host header, and you specify the full URL. In this case, it's www.net/csumass.edu, or whenever you request something from the browser, using the browser, it will automatically add this part to the request. Why is it not in URL? Who knows? But this is how the protocol works. The rest of the headers, they kind of, like if you look what the actual browser is sending, what kind of information, you probably see much bigger picture, and I think I put the example of some web page that I was playing with. But there's just some of the information is about user agent, some information is voluntary, like for example this user agent thing. Some information is related to what kind of encoding I would like to accept, or if I'm very simple application, I may only accept the plain text to view, and if you have multiple versions to give me, you're gonna have to select me something else. Some of the items define if you can support not encryption but compression of some sort. So data is kind of optimizing how much data we forwarding through this TCP pipe, and some other things. So one of the important part regarding HTTP 1.1 is the last one, is this keep alive thing, or like a connection and keep alive, simply meaning that for this request, I'm expecting the server not to drop my connection immediately after request being fulfilled, but rather keep it for some short period of time. And I'm kind of advising the server to keep it for at least 115 seconds. I don't know whether it's the current practice, but this is just some advice. Advice not necessarily going to be followed by the server, but it can be followed. Now again, important part of the HTTP exchanges. So the stuff that I just talked about, this request line, header lines, are the body of the, sorry, not the body, but the body of the header. And because you can include multiple headers, you still need to indicate to the server that the request has ended. And just to kind of get back to the project one and I talked a little bit in the previous module. This is what we're doing here is a TCP stream. And in TCP stream, you send data and the server receives data. There is no kind of indication but from the server of the client perspective, using just this low-level send and receive calls, that the message has ended or message has not ended. So you have to have this explicit indication that you received something, like this is the end. So the effective is something, you have to indication this is the end. And for the each line, this /r/n is indication that the specific line of the kind of entity has ended, and you have to process in different ways. So for example, the first line have to be this get or not get or like put or something else, and the following lines have to be in the format of the keyword, the colon, and some value. But we still have to finish this part, because if we don't finish this part, the server wouldn't know that it needs to start processing. So therefore, you have to add this so-called blank line, just like /r/n, just to indicate that you no longer have any more headers to add. At this point, if the request is simply get, then the server can start processing this request and fulfilling this request, and do whatever it needs to actually return either data or respond that this data doesn't exist or do something else. But that's kind of important. There's indication of the ending of each line, so it's going to do preliminary processing maybe, or just to collect all those headers, and then empty line with the /r/n to finish the whole header and start processing. And the same process the same format you will see for the SMTP, also for the response, and for some other protocols that we maybe gonna look in the future. As for the methods that are available besides get is the post. So difference is simply with get you're only trying to get information, but like sometimes you actually need to send some of the data. So for example, if you're trying to log into your bank website, you need to send the login and password. Or if I'm uploading this video, I still need to upload a lot of data. So this done kind of in form of a post. And I'll talk a little bit more for the post in a bit later. And header, like this head function is quite a bit cheaty thing. It doesn't really actually request for the resource, but rather requesting for the meta information about the resource. It is useful in some cases, but there's special circumstances when you really want to do that. For HTTP 1.1, they actually added a few more things, but essentially it's the same thing. The format is exactly the same. It's just additional semantics that is being associated with that request. And for the post, I would like to emphasize, there is this optional body part. So this optional body part is something like for the get it doesn't exist. For the put it may exist, where you can put any amount of information in the special encoding, and then also finish that part with the special encoding as it defined by the protocol. Let me move to the response. So the response is quite similar, in a sense, quite similar to request, with exception that instead of this request line is just indication of the status line. So for all responses you'll see the status line. It's indicate what the protocol being used, and the most important is this error number and whatever message afterwards. So for the HTTP purposes, everything within 200 range is a good code, meaning that the request has been fulfilled and everything is fine. And some other numbers like 404 that you probably seen before, meaning that there's no request cannot be fulfilled because this page doesn't exist. And I think there's a few more codes few more common codes that I will show you in one of the next slides to indicate some form of an error. As for the header lines, so the header lines, they include different information, obviously, and really what they return depends on a specific server implementation. Sometimes it may return you almost zero information in there. Sometimes it can return you some information like date of the file, whether the server is running, like when this file that you returned been last modified, and some other random information. For HTTP 1.1, there are a few important parts. So one of them is this content length. And keep alive is just indicating that the server accepted the advice from the client to keep it alive, and just saying I will time out within around from 10 to 100 seconds. or milliseconds. I don't know exactly the unit for this one. But effectively, from the client perspective, you now can just either request faster, or if you realize that the connection has been closed, you just have to reestablish the connection. Finally, there's exactly the same blank line to indicate that there's end of the headers, and now the data starts, and then there is a data. So the important part, and the reason I mentioned why the content length is quite important for HTTP 1.1 when we have keep alive connection, when we have the connection alive, like, or persistent connection, is the fact that you still need to have idea how you, where is the end of the data. Like if it's a non-persistent, so the end data is at the end of the connection, so that you don't really need to specify this content length, and you start receiving data, and until the when connection has been terminated, then this is the indication that everything was received. If you have a persistent connection, then the problem is you start receiving, but maybe there's at some point you get into response for the second request, or like there has to be indication that something has finished versus something else you start receiving, or if in a simple case, to differentiate the end of the data and the fact that just something bad happened inside the connection, inside the network, and it just simply stopped receiving data. Yeah, so I hope you got this concept. So with HTTP 1.0, we don't need any content length, and we're directly using end of the TCP connection to indicate that data has been finished. With the HTTP 1.1 and persistent connections, you indicate with this content length when you need to stop receiving data, or like when the data has finished and you can move to another request. It's a little bit different with the pipelining, but I'm not going to be really talking about that one. And for playing it manually, so you can actually, so the browsers on themselves doing all these operations, they connect to server and issue the HTTP request, give a lot of headers, and then process the response. Given it's a very human-y friendly protocol, you can actually connect to the servers and start requesting and evaluating the protocol on your own. So for example, let me try to do it manually. So for example, I can try to do this connection that I just mentioned on the slide. So telnet google.com and 80, and telnet command, just for your information, is simply establishes TCP connection and giving you opportunity to send some data to the server and effectively receive data from the server. I mean, logically it's for the remote operations, but you can use it in simplest cases for the simple TCP exchanges. So for example, what I'm doing is trying to establish connection to the IP address represented by the hostname google.com and to the port number 80. It just indicated that I got connected to the server, and the server now waiting for some input from me. And what I'm gonna try to do is to get the slash, meaning whatever represented by the slash, or index HTML, and then as indicated I want a HTTP 1.0. And in this case, I will omit all the headers. As I said, they're not really required. And to omit all the headers, I need to have a blank line. And every time I'm pressing enter using the telnet, it automatically adds this /r/n. So right now, if I press enter again, that will be indicating that it's a new additional line, like empty line, indicating the end of the request, and everything is supposed to be finished, and I will supposed to get some response back. And as you can see, I actually got tons of the output. I cannot really process as a human this output. I see there's a lot of CSS involved in the process. But what I wanted to highlight is just part of the header part. So as you can see here, we got the response part. There's a status code 200 saying everything is fine. The server said, oh, it satisfied this 1.0 connection, and it's got some information about the data and some extra stuff. Then there's again this blank line that I indicated, and there was some form of a content. As we can see, there is no content length because I used 1.0, and the end of the connection was indicating that this is the end of the file. Okay, so I hope you can try to play it with the kind of manually. So that would be your kind of indication that you actually watched this lecture. So I'll put a small assignment for this part. So please play and post the kind of try to telnet to some simple web server, not necessarily Google.com. Please pick some unique web server that you know about, and get requests for example, to slash using HTTP 1.0. So just for your information, I already tried at home. Somehow this time I got a completely different response that I got the previous time. That's interesting. And I think one difference was from the previous request. Last time I tried to type google.com, which indicated to Google that my URL was HTTP or HTTPS/google.com. And for some reason, Google decided that it doesn't like that you type in just google.com, and it wanted to include this www.google.com, which many users, many web applications actually want you to move to some different URL, which is considered canonical. But again, this is really depends on specific implementation, specific policy of the web server, or web administrator, or whoever writes this web application. And as I mentioned, there's a few very common error codes for you to remember, like to remember the high-level detail. All 200s are good ones. Anything that is not 200 is not good. There are a few less bad and like really bad, but in any case, so 300 or some related to 300s, it's lesser bad stuff, which indicates is something not right with your request, but usually the process can continue. So for example, if it's a 301 indicated moved permanently, most likely there's indication where it was moved, and the browser can technically request it again using this kind of hinted location, hinted URL, and everything will be fine. Everything else, starting from 400, 404, and others, indicates something really, really bad happened, and most likely not going to be resolved. So 404 I already mentioned, it's resource not found, which means what you're requesting doesn't exist. And bunch of 50 something or 500s errors indicate something really bad happened either to the server, or something wrong with authorization, or something of that sort. So this is just another example of HTTP headers that I played before to see what's actually existing. Regarding why, again, after you, like in your homework, like not homework, but rather in this lecture assignment, try to just briefly describe why do you think either browser send a specific header, or why the server reply with that specific header. I'm not expecting you to give me like complete detail, just as of right now, just give you some high-level details. I think I already described a few of these headers, some of them just try to guess what those for. And for the exploring the content of the web pages, I just want to do a small demo highlighting like how in modern browsers you can actually see a lot of stuff, what is happening underneath. So not just see the content of the web page, but rather see like how many exchanges happened, what was requested, how it was requested, what was the kind of request, what was the response, and so forth. Let me switch to a different window. So for example, I went to kernel.org website, and most of the modern browsers, I'm kind of very familiar with Chrome, but all others also have this function. You can open the developer console. So for the Chrome, it's either you do open this developer tools here, or press the buttons. I think it's Command Shift J, or Command Option J. For Chrome and Firefox, it's you can find it's in developer somewhere, developer menu. You can open some form of a developer tools, but all of them have this function. And what's important with respect to this lecture, there's a network tab indication here, where you can observe what exactly is happening with the network. Because we just opened this tab and we didn't do anything yet, there's absolutely nothing. But as soon as we reload this page or go to some other page, we'll see a lot of information. So for example, if I click on About, you immediately see there's a bunch of things that start to get requested. And if I try to just move it away and open it in a bit more interesting fashion, you would see that we requested this About page, which somehow requested a bunch of other resources, and then somehow more resources got pulled in. And this would be related to future questions I think we cover in this part as well. There's a few things that you can notice here. So this one is a waterfall thing highlighting the time sequence when things got requested. So as you can see here, there was a request for this About HTML page. I don't even know. Oh, there's even a description of what exactly happened in those different stages. So there was initial connection that took a lot of time to set up, because you need to send the TCP SYN, like respond, and there's more responses. Then there was yet a little bit more time to actually set up the security part, like TLS connection or SSL part. And then finally, there was only 81 milliseconds that took to download the page. And only after the page was downloaded, the browser was able to decipher what else needs to be requested. So, for example, this picture about the Red Hat community and other things. So it requested all of them basically at the same time. And after those got requested, it figured out that there's more stuff need to be requested. In addition to that, like you still need to pull the CSS files, like the style files. And the style files most likely indicated they need to get some additional funds and so forth. So this is how you can explore the timeline. But the interesting part, you can click on each of them, each of these files, and you can actually see all the stuff that is happening inside. So for example, you can see request headers. So what was requested, it simply hid the fact that it's created this get request. It's part of the first general. So it's not really giving you the ability to see the raw requests literally, but you can see most of it in any ways. And finally, you can see the responses. So there's what kind of headers were included as part of the response. For the preview responses, so you can see the actual content of the response, and timing I already showed you just a little bit more expanded form of these timings. So please try to go somewhere, try to explore different headers, just to get familiar with all those things. So it's not that maybe useful in everyday life, but when you start developing some web applications, you most likely will need to use some form of these developer tools. And one of them is something is go wrong. This network tab can indicate that some resource cannot be fetched by whatever reason, or some resource taking a lot of time to be retrieved. Okay, so that was the end of our quick demo. And just to give you a few more ideas about this in non-persistent and the problem with non-persistent stuff. When we have, so the problem does not really exist when we have to request a single object, but the problem at the same time is I just mentioned in the beginning and just highlighted with my example, today's web pages are not a single object. So they usually contain tons of objects. So in our example, it was about, I think, 20 objects. And if we use this non-persistent HTTPS or HTTP, we're going to pay a lot of prices for different things. For example, for this connection establishment, you just saw an example that it took the longest amount of time. And if we had to establish a new connection for every single object, our download time with the time to download the whole page wouldn't be measured in milliseconds. It would be measured in tens of seconds, because every single time we would waste like 160 milliseconds to set up connection, then 80 milliseconds, and just giving back with the timing that I just saw before, let me close this one. Yeah, so it was like 150 milliseconds to set up the connection, 80 milliseconds to this TLS. Okay, but barring this TLS, is still 80 milliseconds to request the actual data. But the thing is that the 150 milliseconds would be for every single object in here. So you can basically calculate the time, like if I give you some kind of round trip time between client and server, and the amount of data that needs to be sent out, assuming it's simple HTML file that takes trivial amount of time to respond, literally the amount of time it's needed to retrieve the data would be at least 2 RTTs. It's like 2 RTT plus transfer time, but again, this really depends on the amount of data we need to transfer. And kind of in this example, you can basically calculate how much time would needed to request this page. Okay, so I just decided to ask you yet another question online. Well, just give me this answer. So this kind of the calculation is quite simple in this case, but just try to calculate, try to participate in the whole discussion. So this one is just an additional explanation for you to what exactly is this process. I'm actually a little bit hiding a few more exchanges, like a few more delays, because the host name still needs to be resolved to the IP address, and that's taken yet additional amount of time. But again, for the purposes of the HTTP discussion, let's just keep that out. So effectively, you need to establish connection. You server have to kind of on top of that established connection, the client has to send some request, and the server finally has to respond with everything. So you can kind of do processing and do calculation of all this process. So the improvement that I'm trying to go to is effectively trying to reuse that TCP connection. Look, if we don't need to establish new TCP connection, we definitely can save a lot of time, some amount of time to retrieve that. Sorry. So there's in the sentence mentioned 2 things, like for HTTP 1.0, there's at most 1 object requested over 1 TCP connection. And effectively, you can try to optimize 2 parts. So instead of 1 TCP connection, you could open multiple TCP connection at the same time. That's absolutely possible, and kind of browsers are doing this, or at least they were doing that before. Then you would effectively establish whatever, you have 20 objects, you establish 20 TCP connection, you pay in the same amount of time to actually do this initial exchange to establish TCP connection, and over those 20 TCP connection, you request a single object. That's possible. Unfortunately, kind of each TCP connection uses the resource on the computers, on the operating system especially. So people didn't really like to go ultimately in kind of opening like hundreds and thousands TCP connections. So the browsers usually limit, I forgot how many, but like 3, 4, like very limited number of connections per destination host. So the second optimization is, as already mentioned before, is to request multiple objects instead of 1 within the single TCP connection. And this is effectively what the persistent HTTP is. And just to highlight in which place this persistent actually being embedded. I put a little bit more for the external reading, so I would advise you to at least skim read the RFC 1945 and RFC 2616, just to give idea of how these specifications look like, and maybe you will gain some insights of the HTTP protocol details. And there is one more interesting detail about the persistent HTTP. So there's a pipelining and not pipelining. So one thing is, how to say this, depending on what being transferred. So like, for example, if we're within the same TCP connection, we're transferring reasonably big size data, then we don't need any kind of the pipelining, because we simply open the TCP connection, paying some price, start send one request for the data, pay time, some amount of time to request that data, and then start receiving a lot of data. So and that will be probably like time to retrieve that large piece of data would be effectively our cost. And for the next object, again, we start sending request and start receiving the data. And if the time to send this additional request is negligible compared to the actual data cost, then there's not a big deal. However, if the time to receive the small piece of data, like if data is small and the time to receive the small piece of data is much smaller than RTT size, like because to send the request you have to spend at least half of the RTT, so like you need to indicate that you send the request, and another half of RTT is coming from the other part because you still have to receive the data. So so effectively you send a request and you will get your data at least after one RTT. And if you have like hundreds of small objects, it's kind of not interesting that you send one request, waiting the RTT to get that small object, sending one request, again waiting one RTT to get that object. So people decided to do the optimization. So instead of sending one request at a time, with the pipelining, you can send hundreds of requests and then simply sit and wait until all requests coming in. And this is effectively the highlight on this slide. Sorry, I probably should have shown you this before. So the HTTP 1.1 with pipelining is effectively this process. So instead of opening the connection and start sending request, reply, you can do is send 10 requests at the same time and simply wait for the old data to come in. And because you know how much each data is, because it's indicated by the field of content length inside of each HTTP header, you can simply process those things together. There's still a small complexity to keep track of which response corresponds to which data. Like in the simplest case, it's all responses go in the same order as they were requested. In more complex cases, there's actually a chunking protocol where you can define, effectively you indicating which part of which request being currently fulfilled. But this is not part of HTTP 1.1, but more like a higher level, advanced versions of HTTP. So to give you a high-level summary of what you just learned, so I hope you got quite a good grasp on HTTP. So it's HTTP by itself is this very content-oriented or message-oriented protocol where you always have URL. From this URL, you construct HTTP request of some form, like we either request for the get, or there's a request for put, or some other types of requests. For the URL, I hope remember there's like 4 major parts, like schema, authority, path, query, and there's potentially some fragment ID. Just as a side note, URL works not just for HTTP, but it's also used in other environments. To get you, I give you additional information. So HTTP as a protocol being used not just for the web pages, like it's being actively used as part of so many different things. Like I put immediately remembered only three basic things, like our web pages, video streaming, like YouTube effectively relies on HTTP. Or it's almost like HTML, but it's a little bit advanced version of HTML. If you heard the word REST, so this is form of API for high-level API for applications, but effectively they reuse HTTP protocol to send the commands to somewhere or do some other type of magic. And as part of the HTTP protocol, first of all, remember that there is a very structured way of sending requests and receiving responses. So for the request, there's a first line indicating how you're requesting, then following with the headers indicating some meta information about the request. Like some of this meta information is extremely important, some less important. And finally, there's a separation between this request body and the actual body or the end of the request using this empty line. For the response, there's a very similar structure. There's a first line indicating the status of the response, following with meta information about the response, like some of them important, some of them less important, some of them critical, then separated with the empty line and the body of the response. And the difference between this non-persistent and persistent is with a non-persistent, response is contained within the single connection. Connection ends, the response is gone. With the persistent, you have to, like the server have to indicate how big is the response, so you kind of have to count number of bytes you received. As soon as you receive the right amount of bytes, you consider that was the end of the request fulfillment, like that was the end of the response message, and you kind of done at this point, and you can process the rest as either response to a different request if you use the pipelining, or kind of consider this an error and throw some kind of error if you didn't request pipelining, if there was nothing pre-requested before. Okay, so I hope you're gonna get a good grasp, as I said, about HTTP. This is it for kind of this basic introduction of HTTP, and the next time I will try to introduce you to a few more advanced things that you can do with HTTP, and kind of advanced things about HTTP in general. Okay, thank you, and see you next time.